So hopefully you can see the writing pad. Can you see the writing pad?
Yes, sir.
Yes,
Okay.
sir.
Okay. So let us continue from where we have left last time. So last time, possibly so possibly we discussed about this in the previous class about the derivation of this equation. So we will move forward from this equation and see that how it relates to the concept of incompressible flow. So when you have an incompressible flow, the general perception, so let us write it somewhere here, that the general perception is density is constant. This is a general perception. I mean, if you ask your conscience that, I mean, given the concept of incompressible flow, what first comes to your mind? What first comes to your mind is that it's a flow where the density of the fluid is constant. Now, let us look into the implication of this. So if density of the fluid is a constant, then of course it is not a function of time. Further, if it is a constant, it comes out of all the derivatives, and therefore this boils down to divergence of velocity equal to 0, which we earlier saw that from pure kinematic considerations, this is nothing but zero volumetric strain. Or strain rate, whatever you call it. Okay, so this and this, they are consistent in terms of the conceptual framework. That means if density is constant, you expect that there will be no change in volume of an identified fluid element. This is very intuitive also, that if density is constant, how can you have the change in volume of an identified fluid element? However, we now will look into it in a bit of a convoluted way. That is, the fundamental hallmark of incompressible flow from the kinematic considerations was this one. Now, does it ensure that rho has to be a constant? This is the most fundamental question that we want to see. That rho equal to constant implies zero volumetric strain rate, but does zero volumetric strain rate necessarily require rho equal to constant? So this is the subtle question that we would like to answer. To do that, what we will do is simply we will trace back the derivation of this equation. So we had, so let us write it in the sort of separated from the product rule. That is the one step prior to this. So this was one step backward to this so-called the final form of the continuity equation. Now, this is nothing but the total derivative of density. Now, what we know is that this is the fundamental signature of incompressible flow, right? Zero volumetric strain rate. So, if that is the fundamental consideration of zero volumetric strain rate or incompressible flow, that means this has to be zero for incompressible flow. No doubt about it. It has nothing to do with density. It's a kinematic constraint. Okay. So this has to be satisfied no matter density is constant, variable, etc. If it is incompressible flow, this has to be zero. So that means to satisfy this total thing to be zero, the other term in the equation also has to be zero. That means, in other words, this one, this also has to be zero for incompressible. Not directly but indirectly. Directly it is because of this, but because the total of this is zero, the other term will also be zero. So if we want to relate the kinematic aspect of incompressibility with the fluid property density, the only relationship that is coming up is the total derivative of density equal to zero. Okay. Now total derivative of density equal to zero. Let us say put up an example in a Cartesian reference frame. So what does it mean? So now, is rho equal to constant a compulsive requirement of this? Rho equal to constant is the most trivial condition which will satisfy this, no doubt about it. If rho is constant, all its derivatives will be zero. But to satisfy this, it is not necessary that rho equal to constant. So we can say that rho equal to constant is a sufficient condition for this, no doubt about it. If it is there, then this will be zero. But not necessary condition. That means this can be zero even if density is not a constant. So the bottom line is that incompressible flow need not have constant density. I mean, this is what is so clear that you have four terms, sum total of that has to be zero, but you could still have rho as a function of some of these variables or all of these variables. So for incompressible flow, density need not necessarily be constant. I am repeating this because this will seriously conflict with whatever many of you have believed over years, that for incompressible flow, density has to be constant. And in fact, in many of your problems and other things in previous classes, you had even written statements. If you recall, I see many answer scripts in different levels, so I can understand this. That since the flow is incompressible, density is constant. This kind of argument for solving a problem based on the assumption of incompressible. So that assumption is not correct. You can assume rho equal to constant for whatever reason, but not because it is incompressible flow. But once you have assumed rho equal to constant, you are dead sure that it is incompressible. So let us take a particular example, a bit mathematical, and then I will try to give you a physical sense of this, I mean this type of thing, I mean that why it can happen. That density is not a constant, but still the flow is incompressible. How it can happen? So to do that, let us take an example problem that you have the density is given as k into xy, where k is a constant. So it is given that the flow is two-dimensional and incompressible. Okay. So given that the flow is two-dimensional and incompressible, the question is that what could be u and v, and is it unique? So this is density. You are having to find out u-v combination, and is it, I mean with this just given this consideration, is that velocity field a unique velocity? Okay. So I mean let us try to solve this problem with the kind of mathematical background that I have already discussed. It should be very straightforward to solve this question, but I want to give a bit more insight than just solving a problem for getting an answer. But now let us do that as the primary work. So if you look into this equation, so this we will use. I mean why we will use? Because density is our given consideration, so we will use a density based consideration. So when you have this one, first of all, rho is not a function of time, so this is 0. Rho is also not a function of z. It's a two-dimensional flow. So this has to be 0. So only thing that you have is u into this plus v into this is 0. Okay. So once it is 0, so let us just put the derivatives. So you have u by v is equal to minus x by y, right? So that means you can say that u equal to cx and v is equal to minus cy. Okay. So this is the form, and this has to be compulsively the form. But it is not unique because it is parameterized with respect to the parameter c, which can have many values except 0. So in that way it is not unique, but you still get a form of u and v which needs to be there to satisfy this incompressibility condition. So what we learn from here, that it can be incompressible flow, but density is not a constant. You can check that the basic kinematic constraint of incompressibility it is satisfied. So this is in the two-dimensional, it is c minus c. This is 0. Okay. So that you can see that that is satisfied. That means it is verified that it is incompressible flow, but it is also true that it is not a constant density flow because rho is a function of x and y. In fact, it's a inhomogeneous fluid. So the question is that how can such a thing happen physically? See, mathematically it is well established, but how can such a thing physically happen? So I will give you an example. Say you have let me just make a simple drawing. Say you have an identified region in which you have some liquid. 1. So now there is a phase change. So because of the phase change, you have, say, part of the liquid, one, has got converted into either a liquid 2 or vapor, whatever. So let me just generalize it instead of telling liquid or vapor, because that will add to unnecessary confusion. Let us say that it is phase 1. It is evolving into phase 2. Okay. Initially there was completely phase 1. Now there is a phase change. Say like sort of melting of ice, vaporization of water, like that. Phase 1 is changing to phase 2. So when phase 1 is changing to phase 2, when the domain is partly phase 1 and partly phase 2, phase 1 has a density and phase 2 has a density. So you definitely have rho as a function of position. I mean, at some locations it is a simple step function. At some locations it is some constant, and at some other locations maybe another constant. Or even within a phase it may be variable. But even in the simplest case, it will be a constant rho1 in some location and constant rho2 in another location. Now let us say that rho2 is less than rho1, just as an example. So what will happen? If rho2 is less than rho1, that means the density of this phase 2 is less. So density of phase 2 is less means that with change in phase, it is expanding. Right? Physically, that is what? Expanding with change in phase. So when it is expanding with change in phase, what will physically happen? See, this is a fixed volume that we have considered, but an open volume, not that it's a rigid some tank or something. It's a conceptual fixed volume. So when you have this conceptual fixed volume and there is expansion, that expansion has to be accommodated by a flux of fluid, which whatever is the possibility it will go out of this, because the volume has to be, its sanctity has to be maintained. Whatever was the volume it was containing, now the volume with changing phase is more. So where will that extra volume go? That has to be expelled. So here we are getting rho as a function of, say, x, y, and you have the velocity fields u and v physically. But in totality, these individual phases of this fluid, they may be representing incompressible phases. So if they are see, this does not guarantee that they are incompressible phases. But if they are incompressible phases, then this will be topped up with this incompressibility constraint, or equivalently the total derivative of density. So remember that this physical phenomenon does not require that it has to be incompressible, but there is also one possibility that it is incompressible. And if that possibility is there, these additional things have to be satisfied. That was the kind of mathematical problem that we talked about. So physically, I mean, how it is possible? You can have, say, one liquid phase, another liquid phase evolving. So I mean, it is practical that you will not have any change in volume in the individual liquid phases, and therefore this will be followed. So in that way, it is not it is not unlikely that you can have some variable density in the domain, but still the flow is incompressible. So this is called as variable density incompressible. So for many of you, it will appear like a say golden bowl made of stone. That kind of statement. That it's a golden bowl but made of stone, like incompressible flow but variable density. But the scientific truth is is always stranger than what you could believe. Now the final remark about this is that the conflict between the perceptions of incompressible flow and incompressible fluid. When we talk about incompressible flow, see, the keyword is flow. So our focus is on the velocity field from pure kinematic considerations, because that is what is giving the volumetric incompressibility. So this is the focus. But of course, because this is related to the density, that is also, I mean, you can implicitly relate it with density. Now, what about incompressible fluid? So to explain that, let me just clean up certain parts of this. So the compressibility of the fluid when we say, so here the keyword is the fluid. It means that we are considering one of the fluid properties as the marker of whether it is compressible or not, and that typical fluid property is density. Okay. Now, given the thermodynamic state postulate, the density you can write it as a function of pressure and temperature. These two variables. Imagine the fluid as a thermodynamic system. See, why the fluid as a thermodynamic system is important is because we are here focusing on the properties of the fluid, not the properties of the flow, when we are talking about the compressibility or incompressibility of the fluid. So now let us identify or try to bring out certain physical examples where density could be function of pressure and temperature. So those of you who are from mechanical engineering background have studied heat transfer, and one possible very nice explanation of density variation with temperature is something known as natural convection. So you have, say, some enclosure in which you apply heating. So say from the side walls as an example, so you apply heating. So whatever was the, say, some air was there. So when the air becomes hot, it becomes light and it goes up. So this in the atmosphere also we can see this, that if air becomes hot, it becomes light and it goes up. So one of the key parameters or key factors that is driving this flow is the change in density due to change in temperature. Okay. So this is ideally not always related to the compressibility of the fluid. In fact, even for incompressible fluid, this happens. Like, say, if you have water, even before water becomes say water vapor, you just have liquid water and you heat from the sides in the container, you will see that this motion will start even before it is vaporized. So that means that the physical notion of compressibility may not be very explicitly associated with this, but the physical notion of compressibility is more strongly linked with this. Density as a function of pressure. So we all expect that even with a little bit of change in pressure, the density will change, and if you apply pressure, in fact, it will be compressed. And the compressibility of a fluid or volumetric contraction or expansion coefficient is an indicator of this how much the fluid will compress due to application of pressure, and that depends on the density as a function of pressure. So if you consider the density as a function of pressure, and if that function is significant, that means with pressure there is a substantial change in density. Okay, so that will be termed as a if this is this is what should I say? This is important or practically significant. I mean, because why I am saying is that if density will always be a function of pressure. So the question is not whether density varies with pressure or not. The question is the variation of density with pressure significant or not? I mean, whatever varies, is it negligible or non-negligible? If it is significant, we would normally term it as a compressible flow. Sorry, compressible fluid, not compressible. So it's just two different angles, but there is a connectivity. What is the connectivity? The connectivity is that, see, the total, so you try to look into this. The total derivative, it relates to density as a function of position and time. So the most fundamental question is, why will the density change with position and time? The density will change in position and time because either there is a different temperature or a different pressure at a different location or at the same location with different time, that could have led to the density change. I'm trying to understand the physics of why density will change. I mean, mathematically you can express it as a function of position and time by some algebraic expression, but the question is why it will change. It will change either due to the change in density over time at the same location, or at a different location density is different because of just position dependent pressure and temperature. So pressure and temperature, this could change at different locations, or even at a single location they could be a function of time. So these are all the inclusive possibilities still satisfying the incompressible. Out of that, one specific possibility is that density is not a function of, not a significantly varying function of pressure. And that particular possibility is termed as an incompressible fluid possibility. So in that way, incompressible flow is always a more general way of looking into the role of compressibility in fluid mechanics, rather than just focusing on the fluid property. Because incompressible flow, this kinematic constraint, will accommodate so many possibilities in the fluid property with variations of pressure, temperature, etc., that the consideration of incompressible or compressible fluid only be a small part of that. So that is why in fluid mechanics we mostly discuss about incompressible flow and not so much about incompressible fluid as a property. Incompressible fluid as a property is more commonly talked about in thermodynamics. I mean, not directly incompressibility in terms of density by specific volume, which is 1 by density, because there the situation is more not deviation from equilibrium, mostly quasi-static or quasi-equilibrium, and that is why equilibrium properties are important. Whereas in fluid mechanics, this is the more common focus. So the idea of incompressible flow, I mean, with all these discussions, I tried to bring in significantly more focus and clarity as compared to the idea that you might be having, based on the simple consideration of density, because it relates well with our perception of incompressibility. Now, as I told you that one of the major objectives of the learning the advanced fluid mechanics is to study the same conceptual thing from different angles or from different considerations. So that builds up the conceptual foundation even better. So we discussed about the continuity equation in one of the possible ways, and that was based on a control mass system. That you have an identified lump of mass. So instead of that, we can we get the same thing back by considering a control volume approach for the continuity equation. So this is something which most of you have covered in your undergraduate. If not, doesn't matter, because whatever you have covered in your undergraduate, I mean, my understanding is that it is much better for this course had you not covered. Because if there is a mental block through a prior education, it is very difficult to erase that. It is better not to have an incomplete or wrong prior education. So in that way, if some of you are absolutely not knowing anything about it, I would say that is the best. But anyway, because most of you are mechanical engineering students, you will have some introduction to all this, and we will consider that and move forward. So let us say that you have control volume. See, this is where your this explanation is so important. These diagram, if we do not write anything, this could represent a fluid element or a control volume. But conceptually, fluid element is Lagrangian and control volume is Eulerian. So if we say fluid element, it's an identified lump of fluid. If we say it's a control volume, this is not a fluid. This is a region across which fluid is flowing. So the drawing will be the same. So that is why I have put up the control volume approach. So now let us think about the mass flux. So you have, say, m dot x is the mass flow rate along x, which is through this phase. Now similarly, this is m dot x plus delta x, where the mass flow rate in the same direction, but it is just to recognize that the phase through which this mass is flowing is different, and it is located at x equal to x plus delta x. Similar things, I mean, you can imagine that you have a mass flux of y and y plus, mass flow rate of y plus m dot y plus delta y. Along z also you have, say, through the back face and maybe through the front face. Okay. So now what is our objective? Our objective is to write a mass balance, right? Simple mass balance. So m dot in is whatever is the total mass flow rate that is into the control volume, and m dot out is what is leaving the control volume. So normally, if the flow is steady, then whatever is the rate at which it enters, that is the same at which it leaves. But if it doesn't do that, let us say the flow into this, I mean, across different phases in totality has entered at a rate of, say, 10 kg per second, and it is leaving again in totality over all the phases at a rate of say 1 kg per second. So what is happening? 1 kg per second, 10 kg per second entering and 1 kg per second leaving. So this remaining 9 kg per second, that will simply increase the mass within this control volume over time. So we can say that this is nothing but the time rate of change of mass within the control volume. Why partial derivative? Because the control volume is a fixed volume entity and we are trying to see the change in mass at that, considering all the spatial locations fixed and only change with time. So this is how you can convert a simple physical law to a simple mathematical law. Now, what is m dot in minus out? So you have m dot x minus m dot x plus delta x. This is along x. Then m dot y minus m dot y plus delta y. And m dot z minus m dot z plus delta. So this is something which is equal to the change in mass within the control. So clearly we have three directionalities, and we will consider just one of them and write the others with analogy to one of them. So let us take up the x direction. So what is m dot x? Let us write it somewhere. So m dot x. So what is the mass flow rate through this hatched phase? So this is mass flow rate is what? Density into the volume flow rate. Volume flow rate is the velocity normal to this phase, that is u, because that is only giving rise to the mass flow rate. So velocity perpendicular to the yz plane is only the contributory velocity to the mass flow rate through that plane, and that is the x component of velocity. So u. So velocity into the area. So delta y into delta z. This is the x. So what is m dot x plus delta x? We can simply write that is m dot x plus this one into delta x plus higher order terms in the Taylor series. So this is a simple Taylor series expansion. Why we have done this is because we actually require m dot x minus m dot x plus delta. So what is this? So m dot x minus m dot x plus delta x will be minus of partial derivative of m dot x into delta x and whatever the contributions of the higher order term. So now if you erase it. So if you now write this minus partial derivative with respect to x, let us write the expression for m dot x rho u delta y delta z into delta x. So we can write this as minus this into rho u times delta x delta y delta. So similar will be for the other two terms. So let us write all these together. I will just erase their expressions, and in place of that I will write the simplified form. Whatever we derived for x direction, same thing we hold for y and z. So that will be minus this one for x minus this one for y, because for y component, minus this one for z, and all the terms multiplied by this. Okay. So this is the left hand side. Right hand side, let us similarly write. So I will just write the appropriate expression. So mass in the control volume is what? Density times the volume. We are assuming a constant value of rho locally constant. That means that we are having small delta x, small delta y, small delta z. So what that small region, this rho is like a local constant. You have to keep in mind, so okay, higher order terms also get is right. We have to keep in mind that the objective is to convert this description to the description at a point, because we want to derive a differential equation, and differential equation is an equation which is valid at a point. So to make this valid at a point, the next logical step is we should take the limit as delta x, delta y and delta z all tending to 0. So let me just erase this. So you have limit as delta x, delta y, delta z all tending to 0, so that you have a description at x comma y comma z at time equal to t. So first of all, when they are all tending to 0 or not equal to 0, you can simply cancel this from both sides. In higher order terms, because it contains one of the terms at least of higher order, if you cancel or divide, some delta x, some delta y, some delta z will remain, which in this limit will become 0. And that is why higher order terms are not important. So if we do that, then it boils down to, if you bring all the terms to the right hand side, so you will get this. So again the same continuity equation back, but now purely from an Eulerian approach of derivation. Now during the derivation, there was a subtle thing. I mean, these are certain things which people do not discuss in books or classes, but I mean, these are always little bit of thing, not very very complex things, but should be brought into the thought process. See, when we are considering this phase, at this phase, when fluid is entering at a point, let us say one of the points, there will be many such points, the fluid will have all the components of velocity, x, u, v, w, but why we are only considering the x related matter on this phase? The reason is very clear, that although all these components are here, there very much, but mass flow or mass flux across this phase is only due to u and not due to other components of velocity. And that is why this is related to u and not other factors. And that is why when we consider this phase, only m dot x is coming up, not m dot y or m dot z, because simply there cannot be any m dot y or m dot z across this phase. The second point is that by having such a Cartesian description with mutually independent coordinate axes, we could actually decouple the calculations of flow rate along x, y, and z. Although the velocity vector at the point is very much having coupled vector addition of u, v, and w. But flow rate calculation, we are able to decouple by harnessing the mutually independent x, y, and z components, and physically they are mattering because only one component is mattering for flow through a surface which has normal along that component. So with this little bit of insight, let us say close the discussion today. We will continue tomorrow, and if you have questions, we can take up. uh, please feel free to put up your questions for the next few minutes, which are there, or if you have no question, of course, you are feel free to leave the class.
Sir, after the when we calculated m dot x plus delta x minus m dot x, how were the higher order terms eliminated?
No, they were not eliminated. They are very much there. So the higher order terms will include either say delta x square or delta y square or delta z square. In the x direction, it will be delta x square, cube,
Yes,
etc.
sir.
Okay. Now, when you divide all the terms by delta x into delta y into delta z, so from the unsteady term and the first order derivative term, those terms will be exactly cancelled. But from the higher order terms, if you divide the higher order terms by delta x, delta y, delta z, still some additional delta x, delta y or delta z or their higher powers will remain. And when you put the limit as delta x, delta y, delta z tending to 0, those terms will be 0 for limit calculation.
Okay, okay. Yes, sir. Got it. Thank you.
Okay. Any other question?
Sir, excuse me.
Yes, yes.
Sir, can you please point out the relation like that flux things that I didn't get last thing that sir said? I didn't clearly understood.
No, what I am saying is that, I mean, for calculating a flux, you need to only have that component of flow which is normal to that surface across which that flux is there. So when we have a surface which is normal to the x direction, then the only velocity component which will make sure that there is a flow through that surface is the x component of velocity. And the y or z component of velocity, although they may be there at that location, are not relevant for the flux or flow calculation. So in that way, the mass flow or volume flow, whatever way you call, along these different directions, we can simply consider phases where across the phases only one component of the velocity can be there, and since all these components are mutually independent, we can simply algebraically adapt to these effects for all the phases. Here 6 phases in the control volume.
Okay, sir. Okay, sir. Thank you, sir.
Any other question? Okay, if not, let us close today's class and we will continue tomorrow.